The broadcast is now starting. All attendees are in listen-only mode.
Good morning. Welcome to today's webinar. This is Victoria Beal with the Ohio LTAP Center, and we are so pleased to be working with the ODOT Office of Research on the research results presentation for unmanned aircraft traffic management for Ohio. So a couple of housekeeping items before we launch into the actual presentation. We are attempting to record this webinar, and if we are successful, we will send a link out to the recording after the webinar completes. We will also be sending a link out to a PDF of the slides from today's presentation. There's nothing in the handout box for you today, so you don't have to worry about that. Also, if you have questions throughout the webinar, we encourage you to put them in the question box. The presenters will be addressing your questions at the end, but please submit your questions while the webinar is occurring, so that way you don't lose that question or your thought process once we get to the end. Just put it in the queue and we'll get to it. So I believe those are all the items that I have. We're going to go ahead and turn things over to Matthew and get things rolling. Matthew, all yours.
All right, well, thank you very much, everyone. Pleasure to speak with you all today. My name is Matt McCrink. I'm a research assistant professor here at the Ohio State University Aerospace Research Center and through the Aerospace, Mechanical and Aerospace Engineering Department. I'm here today really representing what was a very large team effort in the design and development of an unmanned traffic management system for the state of Ohio. And so, this is a multi-year effort that really leveraged the capabilities and I think really was an exemplar of a close collaboration between university system and our private companies that we worked with to really stand this up. And so they're listed here at the bottom. I'm joined today by my co-presenters, Sean Calhoun, Managing Director of Cal Analytics, and Paul Heading of Heading Aerospace Systems, working very closely with Drive Ohio and Fly Ohio, and specifically the UAS Testing Center to stand up this program. And so to get started and just kind of jump straight into it today, what we're here to talk about is a critical need that's emerged over the last few years in the design and development of what we call uncrewed or unmanned or traffic management system. And what this is, in its most broad and basic sense, is a means of providing surveillance and deconfliction in the low altitude airspace, right? So this is, you can very broadly think about it as sort of air traffic control for unmanned or uncrewed systems. I'm guessing that most people out there have had some interaction with or are aware of the emergence of these different types of vehicles that are being proposed, both on the small end, so think package delivery type drones, sort of shown at the bottom here, and then the larger end, which would be represented by Ohio's most recent partnerships with manufacturers such as Joby. And so all of these vehicles are notionally slated to perform functions that really exist at low altitudes. And so when you say low altitudes, we're looking at generally less than 1,000 feet is kind of the way to think about this. And so while it might at first glance seem like there's not a whole lot going on down there and there may not be a whole lot of problems in terms of who you can run into, there are a substantial amount of activity that actually exists in that airspace, and most importantly, it changes based on where you are relative to urban centers versus more rural environments. The types of vehicles that you're likely to run into are going to change dramatically. And so that could be anything from, med flight helicopters, moving around the urban areas and downtown environments, or even out in the rural areas, to general aviation aircraft that are, prolific in especially in the rural settings. And then probably most notably, and for those of you who have driven around Ohio's rural environments, there are a substantial number of crop dusters, which for those of you who have seen them have remarkable flight paths and very much exist in that low altitude environment that would pose a challenge for drones or other uncrewed systems that don't have the same means of seeing and avoiding these small aircraft, and it makes a real challenge for operating in that environment. And so the purpose of this research program was to really tie together kind of a multimodal strategy to provide that low altitude airspace deconfliction, right? And so this is the ability to sense other vehicles operating in the airspace, again, at those low altitudes, and then provide that information in a way that is scalable to operators of these uncrewed systems. Okay, and so from all the different types of sensor modalities we might be interested in, so these can be active things like radar, which we'll talk about in just a moment, to passive systems that detect, the RF signatures or other such things of other flying vehicles. Being able to essentially bring all this information through a dedicated backbone to a center that's actually primary function is to provide monitoring and assurance that that low altitude airspace information, that essentially everyone's working off the same air picture, right? So this was, the program was originally started with the notion that we need to design and develop a system and understand how to scale it from a relatively small area along the Route 33 corridor, extending from Dublin, Ohio out to East Liberty, Ohio. What are the tools, sensors, surveillance capabilities that are really necessary to provide that certainty that we understand who is in that low altitude airspace and that we can keep these uncrewed vehicles safe from the manned counterparts operating in that same environment. And so Route 33 is a little bit unique in the sense that it is a smart mobility corridor. So it's specifically laid out with both ground infrastructure to support transmission of information and easy integration of different sensor systems along that route. And so we'll touch on a few of those here today. So just being able to see what's around you is not the end of the story here. There are two other sort of key follow-on components to this that we'll talk about in some detail. So once you can see these vehicles, the question is, what do you do about it, right? And how do you prove that you can essentially maintain well clear or safe distances away from these other vehicles operating in that airspace? And so there's an enormous amount of testing that goes into basically demonstrating that you know where these other aircraft are, and you must capture this information and actually work very closely with the regulatory agencies that govern low altitude airspace, in this case the Federal Aviation Administration, or the FAA. So that was a very close partnership that emerged and evolved over the course of this research program. I'm proud to say that Ohio is really leading the charge in being able to have been partnering with the FAA to design, develop, and implement policies that are going to allow these types of operations to occur. And then finally, one of the things that we're real cognizant of when we went through in this process was essentially not dumping a technology on a community, right? We didn't just want to show up with these vehicles and set them off to the races, and regardless of what the community's thoughts are about how we would actually operate these. And so one of the other key components of this research was how we performed the community outreach and how we demonstrated both the capabilities that were enabled by this system and the potential for providing both life-saving functions and a whole list of opportunities to essentially transit between these urban and rural centers in Ohio. And so with that being sort of the broader vision of what the research was focused on, I would like to delve into some of the details here of some of the technical specifications of how we actually built this system and what we think it's going to take to actually expand this out, again, to provide statewide coverage for Ohio. And so as I led off with, and what I mentioned at the beginning, is that a key component and technical component of this is how do we monitor the airspace, right? How do we really know what's out there? Air traffic control systems that the FAA uses generally isn't looking or specified to be looking at targets that are at the low altitudes that we're really concerned with for the operations that we'll be conducting. We'll then get into a detailed description of what that system looks like. So again, collecting the information isn't enough. It's synthesizing it and providing a unified air picture to users of that system. That's really the critical, I guess, piece of the puzzle here that, again, Ohio is leading the charge in. And then I'll talk about a couple different demonstrations that we did on things that we can use the system to enable. And then again, that last piece is the working very closely with the regulatory agencies to gain approval of these systems and sort of set the stage for statewide expansion, but also again to lead this the nation in understanding what are these capabilities, how do we need to document these capabilities, how do we need to design these capabilities such that these systems can work together. So just as a very brief overview, we mentioned that we designed the system originally to extend along Route 33, the Smart Mobility Corridor. So that extends essentially from downtown Ohio and very near the ODOT headquarters, all the way out past East Liberty, Ohio, and Marysville. And so one of the early design decisions that was made as part of this program was to look at sensing techniques that would allow us to detect non-cooperative aircraft. And so non-cooperative aircraft in this case, for those of you who may not know, refers to vehicles that are essentially not actively transmitting their location via ADS-B, which is a sensor system that equipped on aircraft that essentially provides its GPS coordinates to other aircraft and to other ground-based sensors. And so there are a fair number of them out there, and the coverage for ADS-B isn't necessarily guaranteed, especially at the lower altitudes. And so we were looking for a sensing system that was be able to actively track those assets at low altitudes. And so we landed on using low altitude radars. And so what you can see on the right is a picture of essentially where those radars are. There's one at ODOT headquarters, as I mentioned, one at the Ohio State Aerospace Research Center, and out on a Marysville water tower near the downtown center of Marysville, Ohio. And so those rings essentially represent the coverage volumes at the altitudes that we're interested in, so you can kind of get a sense of what the radars can see. So these are very long range detection capabilities, which is one of the key enabling technologies that we brought to the table for this program. So this is an image of what they actually look like. So these are three-dimensional radars, so they provide both essentially range and azimuth and elevation information of where those targets are, as opposed to a 2D radar, which would just provide essentially latitude and longitude coordinates. And so again, we really want to understand where those targets are in a three-dimensional environment so that we can understand where how we can better deconflict targets that are at low altitudes versus those that may be at higher altitudes. Again, these radar systems are not that large. On the bottom left there is a picture of us installing one of these. So these are actively electronically scanned array systems that do provide coverage out for 15 to 20 miles, depending upon the setup and altitude of which it's installed. And so what we were able to do with these systems once in place was really to look at where is the air traffic that's actually moving around in this environment. And so this was a study conducted over a very long period of time that was looking at, in this particular case, reinforced radar tracks, which are those that actually correlate well with ADS-B tracks, or the cooperative tracks. We also did this for non-cooperative tracks as well. But you get a sense looking at this that it very much overlaps with traffic that exists at Ohio State Airport and Columbus, CMH, as well as a hotspot around Marysville for the Marysville airport as well, which is primarily general aviation traffic, right? And so with this in mind, you can really get a sense of sort of where these vehicles are moving and how we can design routes and paths for uncrewed systems to operate in this environment with a maximum likelihood that they won't encounter this traffic moving around. However, it's not just as simple as putting a radar up on top of a building. One of the key challenges in doing this is that when you point a radar system into ground, it will see everything. So this would be traffic moving along the ground. The joke that I made is that I had one of the best traffic displays in the state, right? So I could see the sides of 18-wheelers moving along the interstates very well. They're very nice radar reflectors. And so there were some key technologies that we need to develop and work on as part of this program to help us filter out and understand where those false and nuisance tracks were coming from. And so one of the ways that we did this, and I think one of the interesting exemplars of partnering with the community, was actually to develop surrogate radar models. So these are models that can essentially predict what the radar should be seeing. And the way that we actually tested this was in partnering with our crop dusting community. It was a really fantastic partnership. We worked with them to install data tracking units on their aircraft and asked them to go essentially spray fields in the vicinity of the radar systems that we were developing. And using that information, a very unique data set, we were able to essentially develop models that allow us to track very challenging targets moving very quickly at low altitudes. And so this paved the way for developing machine learning and AI-based algorithms to declutter and remove some of those spurious tracks that we were seeing at those low altitudes. And so what you might start out with is something like the raw radar returns on the bottom left, be able to identify clutter highlighted in red in the center, and then removing it from the air picture, again, providing you a much cleaner idea of what, again, is around you in that airspace. So this isn't, what I'm talking about here is an active radar system. So an active radar is one that actually emits energy and receives it in the same location. So you've all seen the spinning radar dishes at some point around. They're sort of ubiquitous at this point. But a new technique and technology that we developed as part of this research program was also a passive radar system. And this is a really interesting and fascinating system that actually relies on what we call illuminators of opportunity, right? So that's other things that are emitting RF energy. So think FM radio transmitting stations, digital television antennas, et cetera, right? Things that provide other RF illumination of the environment. And so what we did was build a system that can actually use those illuminators of opportunity and measure their returns and understand, essentially develop a equivalent air picture as what the active radar systems do. Now, why do we want this? What's the advantage? Well, the fact that it doesn't emit means that there's zero spectral congestion. So it means when we integrate this into a community and into an environment, we're not trying to transmit anything. We're not stepping on anybody else's toes, and we're not causing undue interference by putting high-powered radar systems in critical environments. And so it's also, generally speaking, if matured to completion, is a very low-cost system, again, because it doesn't have that high-power array system with it. And also, it's also not actively broadcasting its own location, right? And so there's some really unique advantages to this system, and one that I think we're really proud to develop as part of this research program. And again, this is something that can leverage existing transmitters of opportunity with all of the different digital and high-powered transmitting stations that are stationed around the state of Ohio. So unique geometries here to be able to do this. And some of the early results and testing that we've done with it do show an ability to really track flights at different altitudes and do microdoppler signatures that allow us to actually identify the characteristics of those vehicles. So I think one of the most interesting aspects of this that I saw is when an aircraft, a Southwest aircraft, was coming into land at CMH, we could actually track its engine fan speed using this. So I think very accurate and very interesting technology, again, without having to emit any additional information, right, or signals. So these are some of the means in which we're able to monitor that low altitude airspace, right? So how we were able to detect what was out there, what's moving around in that low altitude environment. And the next step is, how do we bring this all together, right? So how do we provide this information to a centralized service that both can make sense of it, correlate it, stitch it together, and understand what services are available at all times. And so with this, I would like to turn it over to our partner, Sean Calhoun, to talk about the development of the UTM architecture.
All right, thanks, Matt. You can go to the next slide. Yeah, so the UTM concept was originally developed by NASA as a concept for solving the low altitude uncrewed aircraft traffic management system. And so the initial concept identified potential roles and responsibilities across, the FAA, potential local state governments, operators, and service providers, as you can see in the figure on the right. A lot of the initial development focused on information exchange between the UAS service suppliers. So that was basically, they set it up as a federated system such that operators could partner with individual USS service providers, and the main goal or the function of the USS was to provide the operational volumes of these vehicles that they were going to be flying and exchange them across with other USS operators to do a strategic deconfliction. So, if I wanted to plan an operation, I would submit my flight volume, my time, altitudes to the USS. It would exchange that with all the other USSs and determine if there's already a planned operation in that area, in which case it would notify me of a conflict, and I would have to change either my time or location. So again, it's all based around this federated strategic deconfliction concept as the primary layer for the initial traffic management. But there are additional other actors and functions in the system, right? So you can see at the top, there's block for supplemental data service providers, SDSPs. So that was kind of a catch-all for everything else and other information types that may be required by the operators, such as terrain, weather information, surveillance information to what Matt was describing, any other type of information that the operators and the USSs may need to support that operation. And they also had some concepts in there for the FAA for the FIMS, the Flight Information Management System, and then some role for public safety for constraints and other types of information. But again, a lot of that, really has been left unresolved at this point in terms of the role that the FAA is going to play. Will there be a FIMS? If so, what are the data interfaces? And so we're still kind of at that point where there's some initial deployments of these UTM systems going up, and Ohio being one of them. We're still trying to work with the FAA to figure out what the engagement and what role they're going to play in these systems. Okay, next slide. There we go. So I'm going to talk a little bit about the various systems and services that we did deploy throughout the program. Some funded by the program, others funded outside the program, but then we would integrate it within the ecosystem that we've been building out as part of that program. Matt talked a lot about the surveillance system and that service, which included the 3 active SRC R1400 radars in the Columbus area. We've since integrated a Echodyne radar out at the Springfield Airport, and we've integrated multiple UAVionics ADS-B receivers throughout the state. And then more recently, we've worked with UAVionics to build in a service that covers the entire state for ADS-B cooperative surveillance. So we have a pretty good scalable system that we've been able to work out through this program of adding sensors and then easily integrating that in to the service in a very seamless way. And then all that gets fed into a correlator and tracking system that will clean up the airspace picture. So if it needs to do any decluttering, to Matt's point, it can do that. It will do correlation between the sensors. So for example, if an ADS-B receiver and a radar are seeing the same aircraft, it'll compare those and identify that it's the same aircraft and only broadcast one track, so that the operators don't have to see ghost tracks and multiple targets for a given aircraft. I talked about the UAS, the service supplier, the USSs. So again, that's in charge of doing the flight planning, strategic deconfliction, conformance monitoring, and they were really one of the primary services that would subscribe to the surveillance service for looking at doing more tactical deconfliction of aircraft. We just recently stood up a data synchronization service, a DSS. So that is the kind of the information exchange that allows the various USSs to exchange their flight operations and do that strategic deconfliction. So it provides kind of the network and the data protocols for USSs to provide that information to each other for that strategic deconfliction role. We also deployed a detect and avoid service. So since we had this pretty encompassing surveillance service, all we needed was telemetry data from the vehicles, which we could subscribe to the ground control systems for that. And we had the ability then to feed that information into various detect and avoid algorithms for providing alerts or guidance to the vehicles in case a conflict arose and the vehicle needed to maneuver to remain well clear. That's one of the biggest keys to moving forward with UAS operations in a beyond visual line of sight capacity, where the operator can no longer see the vehicle, is having that detect and avoid capability. And then we fed all that into our operations center that has recently moved to the NAMC out at Springfield. And there they can monitor the health and integrity of all the various services and sensor components. They have the ability to manage and issue constraints out to the airspace based on things like sensor degradations or failures or other responses or events. And they're kind of the belly button for any type of contingency response and the associated coordination with that if there are issues, in that low altitude airspace for these drones. All right, next slide. So we worked, a lot of the effort in this program was figuring out what the appropriate integration was between these different services. As part of that, we did push out some minimum integration requirements for USSs so that they could come in and connect to the DSS that's been stood up, and also ensure that they can subscribe, or any other user can subscribe to the surveillance service for tactical deconfliction. So we've set up and developed integration guides for those services so that as third parties come in and want to use these services that have been stood up, that there's a very clear roadmap for them and data details for them to connect to these systems. We did define some future integrations for real-time telemetry, tracking and sharing, and then some additional information for operation status. So, if a drone has a failure, it can broadcast that, and just a little bit more information in terms of the status of the operation. Next slide. So a little bit more about the surveillance service to add on to what Matt did. This is a picture of showing some of the various tracks throughout the state that we're bringing into the system. We did sign Cal did an agreement with ODOT to provide a AWS hosting for the surveillance service and the correlation service. So part of this effort was setting up the secure bridge connections between the various networks that are throughout Ohio to connect these sensors. So, things like ORNet, if the sensors are connected to that, being able to bridge that to the ODOT network, and then sending that information securely to the AWS service where all the subscriptions would occur and some of the track correlation processing would occur. As I mentioned, we've integrated the statewide UAVionics ADS-B service, so now we can see cooperative surveillance throughout the state. And as I mentioned, we integrated a Echodyne EchoGuard radar system and the Springfield system. Next slide. The USS service. So we did do a few different USS integrations. One of their main requirements to integrate is to adhere to the ASTM interoperability standard and exchange that flight information for strategic deconfliction. And then we also ensure that they could subscribe to the surveillance service for any type of tactical deconfliction. I mentioned already some of the future optional integrations and the integration guide that we stood up. And again, now we're trying to, now that we have the DSS stood up, we're trying to engage with the FAA in terms of, what roles and data metrics do they need or want to see for as we look to scale this. Next slide. One of the big things that we did under this was to stand up a system-wide safety system as a critical piece to the UTM system, also known as in-time system-wide safety assurance. So this basically monitors all the sensors and services throughout the system. So this is showing a figure where we're monitoring all the non-cooperative surveillance sensors so that you can see the 2 radars online, and we've actually had a failure that's in the queue to get fixed at the ODOT headquarters. So you see 2 nominal and 1 offline sensor there. And then with the cooperative sensors, you can see the host of flight stations that make up the UAVionics system, their status. And what this allows you to do is, as we get real-time updates and status of these systems, we can push out advisories and constraints to the systems and to the USSs so that they know if a system is down and they've lost coverage for their operation. And as part of that, we've been working with NASA to evaluate these procedures and these services as we've integrated them together to get a third-party evaluation of our procedures that have been stood up as part of the systems in Ohio, both nominal and off nominal. So we've been working with them as having them act as an operator, and then going through various simulated scenarios using the real system, just simulated flights, and then we would exercise various failure conditions that we've identified, like lost link or a radar or other surveillance sensor fails, and just validating and refining the procedures associated with these services. Next slide. And then lastly, I think this is my last slide. No, I got 2 more, sorry. One of the other services, and Matt's gonna talk about this in a little bit as well, is our DAA service. So this is basically with the surveillance service, we can bring in all those feeds and provide system-wide DAA services for the operator. So, we can alert the operator through our USS anytime a crewed aircraft, a manned aircraft comes within a certain proximity of that aircraft. We can provide various alerts and warnings to the operator to take appropriate action to avoid that aircraft. So we're working right now with ODOT and the Hilliard Police Department to use these services for their BVLOS operations and approval. And we're actually going through a FAA service approval for this detect and avoid service as part of their near-term approval process. So if we go to the next slide, I'll talk a little bit about that, and then Paul will get into a little bit more detail on this as well. So the FAA did not have a process for approving services. Most of their approvals and certifications have always been historically for manned aircraft or crewed aircraft at the aircraft level. Well, with this federated UTM environment, and there's all these third-party services, they start to figure out a way to provide review and approvals for these third-party services, whether it be surveillance services or weather services or DAA services, and have a plan to review and approve those services for use in UTM environments for unmanned aircraft. So this is the process that they stood up. I think I'll let Paul talk a little bit more about it in his slide, but I will let you know that with our DA service, we're kind of at the phase 2 piece right now, where we're starting the safety risk management process, where they will provide that the FAA agencies and groups within the FAA will provide scrutiny on the service and ensure that it's robust enough for use. I think that's my last slide.
Yes, thank you, Sean. I appreciate it. So in the interest of time, I'm going to speak very quickly about some of the demonstrations that we did as part of this. So as Sean mentioned, one of the first real flight demonstrations that we did was of their detect and avoid system in service. We did this in close partnership with ODOT and some of our flight vehicles at the Ohio State University. And so in the top left there, you can see some of the quad rotors that we used, and ODOT had a similar capability that we were able to stand up and basically demonstrate that within that particular flight area at the Transportation Research Center, that the systems and services that Sean mentioned from the DEA instantiations were able to communicate with the vehicles, communicate with each other, and provide tactical guidance in terms of how to avoid conflict in the airspace. And so this is a really wonderful real-world demonstration of actual vehicles flying. We also extended this to include crewed aircraft as well. And so in this particular case, I was the guinea pig, if you will, in the aircraft. And what I wanted to highlight with this photo here, so this is an image I took out of a Cessna 172. I knew precisely where the UAS was operating. It had a strobe light on it. I could see some of the surveillance feeds coming into the cockpit, and I never saw it. I knew right where to look and knew what I was looking for and could not see it. And so I think that really, to me, sort of highlighted some of the challenges with integrating these vehicles together when we're not guaranteed that there's ever going to be essentially visual connection or the ability to really spot them. So that I think is an exemplar of what it is that we're trying to do with this research program. And finally, one of the large demonstrations that we did was essentially what we can do with these vehicles and these services in support of the ODOT mission, the broader mission throughout the state of Ohio. And so we coordinated with local police, fire, EMS, crew wrecking, recovery services to demonstrate a quick clear operation. So this would be something that would occur when a semi-truck, for example, crashes on a freeway. And so with this, we were able to, again, deploy our UAS in close proximity to this accident scene, aided by a connected ground vehicle provided by the OSU Center for Automotive Research car. And so in this particular demonstration, what we were able to leverage was essentially connected ground vehicles integrating with our system as well to provide essentially information that indicated that there was a crash. That information was relayed to the UAS through the systems that Sean had just mentioned. And then those UAS were autonomously deployed to both visualize the accident scene and also provide critical insight for first responders on the ground to understand what it is that they were walking up to when they arrived on scene at the crash. And so, again, this is a very highly integrated demonstration and exercise that really highlights the capabilities of the UTM system for enhancing safety and awareness in these complex environments. There is a wonderful video that ODOT put together. I will link it in the video description, but I'm going to skip it for the sake of time at the moment. And would like to turn to the last part of the puzzle, which is how we engage with the FAA to work through some of the challenges for regulating our system and being able to do advanced flight operations. And with that, I'll turn it over to Paul Heading.
Thanks, Matt. So the regulatory landscape, we can go to the next slide. Thank you. The regulatory landscape back in 2018, when we first started the US 33 Smart Corridor Development Program, it was very limited and very restrictive. At that time, Part 107, which was the general operating and flight rules for small unmanned aircraft systems, it was released in June of 2016. It was only eligible for aircraft that were 55 pounds or less, flying at 100 miles per hour or less, and the operations were limited to 400 foot above ground. And so in addition to that, the regulations themselves were restrictive in that they only allowed for visual line of sight operations and didn't allow for flights over people or moving vehicles. And so this, as we're, with this program that we're developing is to get us to the point where people can operate beyond visual line of sight and operate over people and moving vehicles using our radar systems. This is a hurdle that we have to overcome. Luckily, in Part 107, it does allow for waiving of certain regulations. Specifically of interest to us is the 107.31, which is the visual line of sight requirement, 107.39, which is the operations over people, and 107.145, which is operations over moving vehicles. And so this allows us to submit a waiver application into the FAA with our safety case and our procedures and have them approve it. It's limited to I think it's 4 years now, but it would allow you to operate in a more advanced operations and helped us in a way towards establishing BV loss in the corridor. So the other approaches are under Part 91 rules, which are typical general aviation rules or manned aircraft rules. Normally, you wouldn't be operating under that unless your vehicle fell out of the eligibility of Part 107. And so there you would pursue exemptions under Part 91 to fly those types of operations. And then there's also COAs, but COAs are limited to non-commercial operations. So they may be adequate for first responders or public operations or flight testing of commercial commercial operators, but they wouldn't be restricted from doing actual for-hire operations. One of the things that we found is that many of the organizations don't have the maturity level to develop all the necessary documentation and procedures that they would need for a BV loss waiver. So one thing that we did is put together a user manual for the corridor, and this not only highlighted all the information about the corridor, the general area that they would need for putting together those types of documents, but it also spelled out what they would need to submit to the FAA when they did pursue a BV loss waiver. And so this was a means of how to operate in the corridor, but also guidance on how they could develop that maturity and get to the point where they could submit a waiver into the FAA and get approved. So the FAA is very slow at developing regulations, and not much has changed with regard to 107 operating rules. There's been some amendments, some that haven't been very helpful, especially with the operates over people and moving vehicles. But the FAA is also working with the industry, with programs like ourselves, through this ODOT corridor, as well as standards groups to really identify what the true risk is in these operations. And so what we're seeing in some of these waivers and exemptions are more advanced operations that they're allowing to approve, and eventually, it would go towards rulemaking. What we do know is that Part 108 is another general operating rules for more advanced operations that is currently in development, and then we're expecting that the NPRM will come out later this year, and this would help to streamline BV loss operations. And so this would be a huge benefit for our program as well as the industry as a whole. Next slide. So like I said, the ODOT has been working with the FAA to help them identify true risk in many of these operations. And one of the things that we talked about, there's a limitation in the regulations. So there's a general operating rules, but as Sean mentioned earlier, there was no means for approving services. However, the ODOT was vital in pushing the development of means of approving or accepting of these service providers. They worked with the FAA through AEROS, under AEROS's PSP program, to help establish a method for reviewing the roles and responsibilities between a service provider and the operator during a waiver submittal, the waiver approval process. And so the Section 377 of the FAA Reauthorization Act of 2018 required the FAA to begin evaluating these UTM services in order to determine a regulation regulatory pathway for approving services. And so ODOT's influence has been heavy in their evaluation of that through that PSP program. The slide you see here is a slide that was presented to the FAA as a means of pushing a paradigm through that would to allow the FAA to evaluate the roles and responsibilities between a service provider and the operator. So that under this initial paradigm, the operator is responsible for ensuring the safety of all aspects of the operation, including the service provided. However, during this process, we started to carve out the roles and responsibilities of the service provider and implemented a service level agreement that the service provider must meet to ensure that they're meeting the safety level that the operator is expecting. So we're starting to carve out those roles and responsibilities in order for them to start establishing more of a regulatory process. Next step. This Section 376 of the FAA Reauthorization Act of 2018 required the FAA to develop a regulatory pathway for the approval of UTM services. The proposed process was split the responsibilities, ensuring safety of the operation between the service provider and the operator. Upon completion of a waiver, the operator would receive a waiver, and the service provider would receive a letter of acceptance or authorization. The letter of acceptance would be used to streamline the process for future waiver submittals with a similar CONOPS without the FAA having to reevaluate the service. This could be also used by other operators submitting a waiver with a similar CONOPS and utilizing that service in a similar way. So this is a predecessor to what the FAA eventually did come up with, which is on the next slide. The near-term approval process. So in reality, the ODOT's program was heavily involved in how this was established and is almost in line with what we had proposed prior to the FAA really having any sort of process in place. So I think there's a lot of credit that we can take under this program for what is being done here near term. So in mid-2023, the FAA formalized this process that they called the near-term approval process, or NTAP. This is a process that the FAA will use to continue to evaluate roles and responsibilities of service providers as they work to develop the formal regulations. So service providers' eligibility is restricted under this program. The service provider must be mature and ready for the process. They must have a champion operator who's also mature and ready for the process as well. It's developed, this near-term process is developed for just low-risk operations, and then the operation must also be limited to a specific low-risk geographical area. So it does have its limitations. It's part of the FAA's process to evaluate how this initial process as they continue to develop rulemaking. So the process does provide a near-term operations prior to rulemaking, similar to like the waivers. So the service provider receives a letter of authorization for their service, and then that can be used to streamline additional operational approvals for other operators using the similar CONOPS. Next slide. And this is the process, the NTAP process. There's an intake process that's really evaluating whether the service provider and the operator, the champion operator, are mature enough and have the documentation ready to go into the NTAP process. And so there's a number of documents that have to be developed, a con-use document that's really identifies the roles and responsibilities of the service provider, and then a con-ops document is the operator's document on their roles and responsibilities and their specific operation and how they're going to utilize that service to address specific safety issues. And then they go into an SRM, a safety review panel that is the outcome of that. That's typically what is happening under a waiver approval process where AFS is reviewing that whole waiver package and then determine whether it meets the risk level that they find acceptable. The SRM is the process of doing the same thing, but looking at the roles and responsibilities of the safety provider and the operator separately and combined, and then the outcome is a SRM document that will be submitted in to the waiver and then again reviewed by AFS, but AFS with that SRM document knows that they don't have to reevaluate that the service provider's information because it's already been done under the SRM board. The outcome of that is the operator comes away with a waiver, and the service provider comes away with a letter of authorization that, again, they can use with other operators pursuing similar waivers. Next slide. So,
we've got just a couple minutes here. If you don't want to make sure we leave a few minutes for questions at the end here.
Yeah. So currently, ODOT is involved in 3 NTAPs. Sean mentioned the Cal Analytics Detect and Avoid services, where ODOT is the champion operator. ONS and Unmanned, I'm one of the co-founders of ONS and Unmanned. We have developed a ground risk service that specifically used for observer people moving vehicles, and ODOT is also a champion operator under that NTAP. In addition, ODOT is pursuing an NTAP for their surveillance services, which would be referred to as like a surveillance service, SDSP. And so that the ODOT Op Center is pursuing those services, that NTAP, and using ODOT Flight Ops as the champion operator. That's one that it still has to be accepted by the NTAP process, but we're pursuing it. And the last slide is regarding waivers. Just to highlight, ODOT just received a waiver that was one of the first of its kind. It was a beyond visual line of sight waiver that included observer people moving vehicles without a parachute. So the aircraft did not have a parachute on it. The only other operator that had received one prior was Wing, and Wing, their vehicle has a lot of redundancy in it, and so that played a part in how they were able to get initially approved. So that just kind of highlights that we completed the phase 1, and we're working on some of these other phases to support the NTAP processes. And that's my last slide.
Excellent. Thank you, Paul. Wonderful. It's an enormous amount of work here in these engagement strategies, and Paul, I think, glossed over. There's a lot that happened behind the scenes there, and so appreciate the work there. So just briefly, conclusions for this particular research program. So what I hope the takeaway is here is that sort of laying the groundwork and the skeletal structure for what a low altitude surveillance system actually looks like, right? So we talked about the different sensors that feed into it, but I think most importantly is the output of the research program is the architecture that Sean covered. And so it's how do these systems work together? How do they play together? And how is that information exchanged in a way that's reliable, traceable, and understandable to the users? And so, what we've developed as part of this work, we think is the backbone that can be used to expand to statewide operations and incorporate different sensors that are really tailored to the environment that they're designed to monitor. So not all areas are going to require things like the active radar systems that we used, but being able to feed that information in a seamless manner as vehicles transit those different areas will be critical, and that's what's provided by that architecture. And then again, as Paul mentioned, none of this really gets off the ground without a really consistent and cohesive integration effort with the FAA to make them understand what are the systems and capabilities that we have, what are these, and how do we leverage that to essentially provide streamlined approvals for operators interested in coming in and operating in the environment, be they public entities such as ODOT, EMS, first responders, or private commercial operators interested in expanding things like package delivery or urban air mobility. And so, again, the output of this program is really that entire framework that supports that. And so we glossed over a lot of the details of how that actually happens, but what I would encourage you to do is pull the final report and the supporting appendices where you'll see all the sort of nitty-gritty details and what you would need to do to essentially leverage the system to potentially support your operations. And so with that, I'll address some of the questions that have popped up in the chat here real quick in the few moments that we have left. So one of the first questions was, did the radar systems identify any birds and or bat movement? The answer to that is yes, yes, and yes. Again, when you point the radar systems at the ground, they do see a lot of clutter and information for everything. And so that was one of the key developments of the program. And it's actually an ongoing FAA research program as well as how to essentially quantify and characterize the clutter that's actually provided by these systems. Generally, for something like birds and bats, the tracks are very short and localized versus something like a truck or other things moving along the roads, you can correlate to that type of environment. But yes, there are some challenges with that. Can this document be given out about what is needed to submit for a waiver in the corridor? Generally, yes, this is something we can certainly work with the UAS Center to help your operation. They've been absolute wonderful partners in both supporting it, standing up, and really, as Paul mentioned, being the champion operator for these waivers, and I think would be absolutely happy to share their sort of best practices with you, depending upon your, what you're interested in doing. And then lastly, there's a question about how the built environment, so these would be the urban centers, terrain and turbulent flows from urban morphology are considered in the UTM. So that type of information was something that would be provided by a supplemental data service provider. So these are going to be people providing additional sources of information into the UTM system. So a good example of that would be micro weather forecasting, and that is a service that the state of Ohio has certainly partnered with and has a real interest in expanding and evolving. And so again, what we built in this architecture is the means by which that information can actually be percolated through the system and provided to end users, right? So we didn't develop that capability ourselves, but we did develop the ability to essentially be able to relay and display that. With that, I will open it up. Are there any additional questions? Please feel free to put them in the chat if you would.
Matthew, this is Victoria. I'm not seeing any other questions come in right now. So
Okay.
we'd like to thank everybody for their participation in today's webinar. As a reminder, we have attempted to record this. If it's successful, we will be sending a link out to the recording after the webinar concludes. We'll also send a link out to a PDF of the slides, and we definitely encourage you to follow up and read the full report once it's posted. So thank you all. You did a great job with your presentation, and thank you everyone who attended. Have a wonderful rest of your day.
Yes, thank you very much, everyone. Appreciate it.
Thanks.
Take care.